Hello everyone. Now that we have learned how to denote a particular queuing system in terms of Kendall's notation, we will now see some general relationship that holds across various queuing systems in general. Okay. So, that means what? Like for example, if we say GG1, we mean that generally distributed inter-arrival times and generally distributed service times with single server or with multiple server queues. Irrespective of that distribution, there will be certain results that holds in general. Of course, as you narrow down to smaller groups of systems, again you may have some more relationship that might hold, but what we are concerned right now is the main one which are hold in such generality, right, either single server scenario or multiple server scenario in general. Okay. Before we get into that, right, let us give the notations that we might use throughout the course, and the notations that we are introducing will be used throughout the course. So, and hence you pay attention to this, like, because later on you will not say what is this quantities are, because this is where you get started. Okay, the first one is this, right. So, this is essentially the number of customers in the queuing system at time t is what we denoted by n of t, the number in the system at time t. So, henceforth we may not say number of customers in the system. When we say a number, it always means it is the customers, and when we say n, it is number in the system. As I already pointed out, system means queue plus service, and this nt in some limiting sense is what we call it as n. Without that dependency on this n is what this nt would be. Okay. Sometimes instead of this nt, like you might also write n suffix t just for notational convenience, because you don't need to write one more bracket to write within this. So, this would also mean exactly the same thing that you might use here. And this random variable, right, in some limiting sense. So, here we have written down in this form. So, that means one needs to make a sense of what is this limiting means. So, basically we are looking at the distribution of n of t in the limiting sense is what would be the distribution of n. So, that is the n that we will be interested in this, which means that when the system is in operation for a long time, okay, then you are looking at the number of system at that point of time. So, that is what is this n in some sense. Okay. And as opposed to number in the system, if I am looking at number in the queue, then the notation would be n suffix q of t, which means number of customers in the queue. It means excluding the ones that are getting served currently at time t is what this nq of t, and its limiting quantity is what simply will be nq. And t will be the time a typical customer spends in the system. T means the time a typical customer spends in the system. TQ is again a time a typical customer spends waiting in the queue. So, this is only waiting in the queue, this is system. So, this means this is basically the sojourn time that we talked about, or system time that we talked about, and this is queuing time or waiting time in the queue. This is waiting time in the system, waiting time in the queue, and its average quantities, right. The n number in the system, this average is denoted by L, number in the queue average is LQ, number the time, the sojourn time t, the average is W, and the queuing time TQ, the average is WQ is what would be the case. Okay. Then this Pn of t would be probability of n of t equaling n at is what we denoted by Pn of t, and this as t tends to infinity, what you would get what you call Pn, and that would correspond to the probability of n being equal to n, right. So, this is what you would say in the limiting sense, or when the system is in some steady state or equilibrium or after a long time of things, that is what you have here. Okay. Now, there will be other notations which we will pick it up as we go along, but the main goal is to specify and analyze this process, the number in the system process and its related processes, because that is how one starts the analysis. So, whenever you are able to describe it for NT, right. So, this will be a stochastic process. So, whenever you are able to describe it for n of t, then you will have a complete description, but many a time that is difficult. So, what one looks at is that the distribution of n, its limiting behavior, which means rather than working at p n of t, you try to get p n, right. If you are able to get this p n of t, and that is what is called the transient solution or time dependent solution, because there is a dependency on this time t transient solution, and if you are getting this, then that is what is referred to as a steady state solution or the equilibrium solution, and that is what would be called in that scenario. So, how the system behaves, whether you want to look at the transient behavior of the system or you look at the steady state behavior of the system, for most of our course we will be concerned only with steady state behavior of the system. Briefly, for the simplest of the model, we will highlight how the transient behavior or how the transient solution can be obtained, and from there you will know how complex is it, whereas it is much easier to work with this. And many a time, like it would be sufficient that if you know the steady state behavior, then what you wanted to know when the system is in operation for a long time, things would have settled down to some level and steady state would exist, and in such scenario you would be interested mainly in this. So, our main interest would be in steady state behavior, with pointing out at one point of time for the simplest model what would be this kind of things means, actually how one would do that thing. But again, this is only like is much easier as compared to this, okay. But many a time things may not be sufficient, that if you know only the steady state behavior alone, that you do not have the complete picture of what is going on in the system, okay. Because there are many systems which never reaches a steady state, and there are even if it does not reach, then how it is getting exploded in some sense can be studied only if you know the transient solution. So, there are reasons why one needs to know the transient analysis or transient solution, but we will not go into that aspects, but our concern would be on the steady state behaviors that we might see. Okay. Now, a very fundamental relationship that exists in queuing theory and which is being extensively used throughout is what is known as Little's law, Little's formula, Little's theorem, whatever you want to call it. Okay. So, that Little's law, what does that mean is what is given by this very simple equation. We remember we have already defined what is this L. L is the mean number of customers in the system, W is the mean sojourn time in the system, and we have not said what is this lambda so far. This is the average number of customers in the average rate of arrivals of customers to the system is what is lambda. So, the average rate of arrivals per unit, how many arrivals is come, this is what on an average is what is we denoted by lambda. So, this Little's law relates these three quantities using this simple relationship. Okay. So, as you know, this L and lambda and W, what does that mean is what is given here. Okay. And this is a very general result and can be applied to many systems, many stochastic systems beyond Q2, and it is basically the conservation, any conservative system with inputs and outputs. Okay. You can use this result. Conservative system means that the ones that does not create or destroy users in between. Okay. So, the generic setting for the applicability of the Little's law Of course, it holds under certain assumptions, but there are a lot of work on with different sets of assumptions and the relaxation of those basic sets of assumptions under which this might hold. Anyway, for our systems this should not be pose a problem, so we will take it as given. Now you have a system which is given by this blue dashed line. There is some a black box, right, and there is arrival happening with rate lambda, and then something happens to the entities which arrive to get service happens within the system, and then they depart. Okay. So, under very generic assumption that the system has been in operation for a long time, it is in equilibrium and no customer is getting destroyed inside or created inside this system, and they leave in the way order they come and so on. So, you will get, I mean, some generic depending upon the system again, some generic assumptions when you hold. So, the generic setting under this such a setting, this Little's law holds, right. So, this is basically was developed or given by in 1958 by Morse, but it was his student who gave the first proof of this law with by the name Little, and hence this is known as Little's law, Little's rule or Little's formula and so on. Of course, there have been afterwards that happened around 1961, and since then there have been a lot of work extending these and generalizing these or relaxing the assumptions and so on. Okay. Now, going further, like to take this up further, like let us denote the certain notations furthermore we will introduce, right. So, we denote by this A superscript k within bracket the time of arrival of customer k to the in the system, where obviously the A k plus 1th customer would arrive after kth customer, right. So, that is what relationship that it will hold. So, this is basically the kth customer time point. So, imagine a timeline here and then some 0 and infinity. So, you are looking at the time. Now, A of t is the cumulative number of arrivals to the system by time t. So, suppose if you are starting, assuming that you are starting at time 0. So, in an interval of length 0 to t, how many arrivals have happened to the system is what is A of t, and d of t is the cumulative number of departures from the system by time t. So, in that same interval 0 to t, what is the number of departures that has happened from the system up to time t, and wk is the time that the kth customer spends in the system. Obviously, like since it needs to be non-negative, and nt, which we already defined, is the number of customers in the system at time t. And what would be this? This would be the number of indices k, number of such k's, such that for that particular k, he has arrived before time t, but he has not yet left by time t. So, he will be inside the system. So, that is what is these two things are representing, right. So, this number of such k's, if you just count, that will give you the number of customers in the system at time t. So, you take first customer, whether this is satisfied. If it is satisfied, he is there in the queue. Second customer, third customer and so on. So, number of such customers you just count and then you will get this. Lambda of t is the average arrival rate during this interval 0 to t, and Wt is the mean waiting time in the system of the customers during 0 to t. This is a mean waiting time, W of t. L of t is the mean number of customers in the system during 0 to t. This is what is the notation that we are introducing further. Now, from this above, you can see that lambda t is simply At by t, because this will give you the number of cumulative number of arrivals to the system by time t divided by time length t. So, this will be the average arrival rate, right, average arrival rate, and nt would be the number of arrivals minus number of departures. Obviously, we are assuming that the system starts at with 0 customer. So, this difference is what would be this n of t. Now, we will also define the following limits whenever they exist, right. So, this lambda of t as t tends to infinity converges to some lambda, and this quantity which is n of t, you know, number at time t, n of s is at time s, and you sum over, integral is nothing but sum, right. So, you sum over this n of t and divided by t would give you the L, which is the mean number in the system, right, in some sense, right. And this is basically W, which we are denoting it by this. Okay, we will understand this how exactly it comes to this. So, we are defining these three limits to exist. Now, when this is the case, we can now give the state precisely the theorem, which is basically the Little's rule or Little's formula, Little's law. If the limits lambda and W exist and finite, then the limit L also would exist and L equals lambda W. So, remember L lambda W is what then we have defined it whenever, and if the limits lambda and W exist, that means this and this exists, then this limit also exists and this equals product of these two quantities is what this result says. Okay. So, of course, for the detailed precise proof we require a certain assumptions and so on, so we will not get into that. So, we will just see like a geometric illustration in some sense. You can think about as a geometric proof also of this Little's law in this manner by looking at this figure. Now, consider the figure where on the x axis you have the time and the y axis you have the customer number, which is first customer, second customer and so on. So, at time 0 you start with 0 customer and you do not have any customer arrival until this point of time. At this point a customer arrives. So, the this one becomes 1 here, where the upper, the blue bar here, right. So, I have to point out here the blue bar here, this part denotes the cumulative number of arrivals, right. So, you can see this here, and this red bar below is denotes the cumulative number of departures that we are defined to be d of t. So, this part is d of t, the upper one is a of t, that is what we are denoting it by these two. Now, at this point the first arrival happens. So, this cumulative number of arrivals is 1 and then it remains 1 until this point of time, and then at this point of time the second customer comes here. So, it moves to 2 and so on this. So, the first customer arrives here, second customer arrives here, third customer arrives here, fourth customer arrives here, fifth customer arrives at this point and so on. So, this figure you will get it. Now, the first customer was in service until he arrived at this point, and since there is no one in the system, so he immediately get into the service, and then his service time, the time he spent in the system, right, totally is essentially up to this, and at this point he departed from the system. So, he departed from the system at this point of time. So, the number of departures became 1 here, and until this point of time, from this point to this point, this customer was waiting in the queue. So, now his service gets started, and then he spent remaining possibly in the service, right. So, at this point he departs. So, the number of departures becomes 2, and the third customer departs at this point. So, he goes here and the fourth customer departs here, and at this point of time there is nobody in the system. Remember, this means there is nobody in the system here. Then arrival comes and then things will start all over again. Okay. So, this rectangle is basically the area, if you think, is what is representing the W1, means the waiting time, because it is a unit length height. So, this is what is the length of the time that he spends in the system. So, we call this as W1, right, and this is W2, this is W3, and this is W4, and this is W5 and W6, W7 and so on it goes. Okay. Now, the difference between these two, right, the difference between these two is what would be the number in the system at any point of time. So, at this point, if you see, there is only 1 in the system. At this point, if you look at it, like the difference between these two is 2. So, at this point the number of the system is 1, 2, and at this point again it is 1, then it is 2, then like it is 1 and 2 and so on it goes, right. So, that is what you are seeing the difference as the number in the system. Now, what you observe here is that observe that the total time all customers have spent the system during 0 to t, that means if there were A of t customers, right, the total time this A of t time customer spends in the system is this, right. You simply sum up all these things, which will be equal to this quantity, because you see that the difference I can represent it as n of t. So, if I integrate this this gap, so if I want this particular thing, I can either take W1, which is this, or I can integrate n of t from this point to this point up to this level with 1. So, then I will get the same quantity as W1, right. So, I can integrate this with respect to this. So, this there will be the equality I have written, but there will be exact equality if by time t again the system becomes empty. Suppose in here it is not the case. So, just to give the description, so I have kept this n of t here. Otherwise, suppose I am looking at, if I am looking at such instances where the system has started with an empty system, it ended with an empty system, this will be an exact equality. If it is not, it will not be an exact equality, but since we are going to look at in the limiting cases, right, as time t tends to infinity, the difference would be minimal, okay, and the proof will go through naturally. So, but do not worry about that part, but you assume, but if you want to understand this how this is exact, you look at instances where the system becomes empty again, and you assume this t to be one such instance and so, right. So, then this will be exact equality, otherwise this will not be exact equality, but things will work out even then in the because we are looking at the limits. Now, so then Wt, which is basically the average waiting time of any typical customer in the system during 0 to t, is basically this total divided by the number of customers, which is A of t. So, that is what will be the Wt. Now, this quantity again we shown that this is equal to this, right. So, this is what we mean, right, in the previous one when we said that we will look at this thing. Then the average number of customers in the system during 0 to t is basically this quantity, right. L of t is, this is the number in the system at time s, I sum it over between 0 and t, I divide by t, then what I will get is the average number of customers in the system during 0 to t, right. Now, this one again I can multiply and divide by A of t, then I will get this expression. Now, if this limit exists, or this quantity is nothing but lambda of t, we have seen, and this quantity is nothing but W of t, as we have seen above, right. So, L of t is basically lambda of t, W of t. Now, if you are taking t tends to infinity, the limits of L and W exist, then this limit also would exist, and the stated relation follows for t tending to infinity. So, this is just an illustration of this Little's law that you might use, you might see here. Okay. So, the proof can be found in different ways in different places, of course. It is more than 50 here. So, you can see many places it is being mentioned here, right, and some variations also people have worked on, and that has been available into this. Okay. Now, let us make some general remark about this particular little law. First of all, you see that this is a statement about long run averages. Okay. So, the quantities are defined as infinite limits. Since most of the results that we are going to see in the course are about infinite time limits, so this is also applicable in such scenarios. Okay. And it requires that the limits for lambda and W to exist. So, this precludes the scenario, right, in which the system is growing without bound. So, system is in equilibrium, meaning that system has not grown without bound, it is in equilibrium, which means it is a stable system in some sense, right. So, that only then in this would exist. So, the requirement that these imply that that condition of stability for the system is in place, that is what it would mean. Third, is basically is a bit more general, that this requires only a system to which entities arrive and from which they depart. Now, it does not worry about what is happening to the system or the customer in the system, the so called the quote unquote system. Okay. In terms of how you are defining the system, different relationship can be derived from Little's law, that we will come in a moment. But before that, we will just highlight couple of things, that is that this formula is, as we said, is valid in great generality, right. If you know any two of the quantities, then the third quantity can be estimated, and you will see like it how it is can be applied in a more general setup. And right, so this is also have been is a special case of more general relationship. It has been proved, and that relates to the most conservative system. So, for example, there is something relationship which is called H equal to lambda g, which is called rate conservation law, and this is a special case of it. So, that is a generalization. And similarly, here these moments are all of first order moments that are being related between the waiting time and the number in the system. The first order moment are related. Now, what if the second order moments or higher order moments can be related? What if, how you can relate the distributions between these two? These are all the generalizations, but we may not require that, and as and when we require, I will just point out what is the relationship that is needed, and we will not require much in our course at least. Of course, if you want to know more on that, of course, we can look into that. Okay. Now, come back to what is this generalization means. Depending upon how the system is defined, different relationship can be derived from Little's law. That is what we said. Okay. So, the most common one, which is what we have written and we have understood so far, is that system includes both queue and the server. So, you have an arrival, a system which has a queue and a server, and to which it departs. So, L equal to lambda w, where L here the average number of customers in the system, meaning in this whole thing, and W is the average time spent in the system, right. So, this is one way of looking at in a more general setup here. Now, suppose look at this way. Suppose if I look at the system as only including the queue, right, then this relationship can be brought down to this relationship, where you are looking at scenarios where customers arriving to queue, they are waiting in the queue, right, and they are leaving for service. So, the departure is actually getting into the service, leaving for the service. Okay. So, if you define system to be this, then this same relationship holds within this structure as well, meaning that for the queue, right. So, Little's law implies that in this particular case, the average number in the queue is related to the average waiting time in the queue by a customer through this relationship, right. So, this is only queue when you describe the system here. Now, the third case, suppose if you define the system to include only the server, right, only the server, right. So, which means that there is arrival happens, there is queuing happens, you are not interested, and you are looking at the rate of arrival to the server, and it departs. Suppose if I look at this particular part as my system, whatever we are looking at the dotted lines as this. Okay. Now, the Little's law would hold true here for this particular system as well, and here L would represent the average number of customers in service, which equals 1 minus P naught. P naught here, remember P n is probability of n equals n. So, n equal to 0 means there is nobody in the system. So, P naught is the fraction of time the system is empty, is basically there is no customer. So, in the long run average, it is what is the fraction of time the system is empty. So, its average number of customers in service will be equal to 1 minus P naught. There is a single server here. So, it is simply 1 minus P naught, that would be the average number of customers in service, which equal. Now, W would represent the average time a customer spends in service. Now, what is that? Which is essentially the expectation of S, where S is the service time, the random service time that you have. So, in this particular case, L equal to lambda W. So, this is my L, this is the W. So, L equal to lambda W. So, that means this is what is the case. 1 minus P naught would be equal to lambda times expectation of S, right. This is a very generic relationship in this. So, this is you use Whittle-Slot to arrive at this particular result. We will use some other way also to arrive at the same result little later. Okay. So, this is what will happen. Now, you can introduce more complexity. Say for example, in this particular case, if there is a blocking, meaning this queuing system has a finite capacity waiting space, this particular queuing system. So, it is what? The finite one. So, we are just keeping it a closed thing here, otherwise we could leave it as open in this particular scenario. So, now there is a finite queue and there is a server. So, if this is what your system, now out of all those arrivals that happens at the rate lambda, there will be some proportion of those arrivals will not be able to enter into the system, and that is what we call blocked arrivals, and PB is the fraction of arrivals that are blocked and hence does not enter the system. So, this is the proportion out of this lambda. So, the remaining proportion of this lambda would enter into the system, right. So, they will be waiting into the system and then go service and departure would also be, this is the rate, that is what we call it simply as throughput to the system, right. Now, this W and L here, remember, like depending upon the scenario, you have to interpret the meaning of W and L here. It is not always number in the system number. So, L and W you have to interpret here. So, here L means and W would correspond to only those customers who actually enter the system. See, out of lambda, only this portion enter into the system. Now, this L and W corresponds to only this. Suppose if I have to take care of this, for these people they do not enter, and if I have to compute waiting time or anything, number in the system also they do not count and so on. So, you need to be little careful when you are trying to interpret what is this W and L here, right. Now, let us look at couple of very simple examples. So, let us take a case of a maternity ward in a hospital, right, and what is your objective? Objective is to determine the size of the ward, and you want to draw, look at the staffing issues, scheduling of staffs or whatever, the staff, how many staffs are needed and so on. Okay. Now, you have a past history data which is there available and which shows that on an average of 5 births per day. Okay. This is what is the record show, and it also shows that in the normal cases when there is not much complications, the 90% of the mothers stay for 2 days and leave. This 2 could also be taken as an average, but we are taking it as 2, everyone is 2, and 10% of the cases which have little complications involved, they stay much longer, and the average length of these 10% of these mothers be 7 days. Okay. So, overall if I look at it, if you put together all, then my W will be 2.5 days, which is what is the time the mother, the expecting mother spends in the maternity ward of a particular hospital, and lambda is 5 mothers arrive per day, right, 5 births per day, that is what assume that 5 per day. So, that means now what would be the average number of mothers who are there in the hospital at any point of time in equilibrium when system has been in operation for a long time is 12.5 mothers. Okay. So, this may not give you immediately like, okay, I will have now 13 beds in my maternity ward, things will be okay. No, it is not the case, right. This is, again you have to remember, this is an average case scenario that we are looking at it. Okay. But this could be a very well starting point of analysis. So, what it gives you is that you do not need to count at each time on each day how many mothers were there in the ward, and keep that data with you, and then you run it for a long time and taking its average. Of course, you will get that, but you do not need, because from these two quantities you can obtain these quantities very nicely, right. Many a time that is how this relationship will be very useful. So, this is one particular case of an operations management problem where you are looking at this. So, one needs to keep in mind the peak arrival rates, right, and the variability in the arrival rates before you conclude anything with respect to how many beds you need in the and how many staffs you need. But you'd always but you also don't want to have like 25 beds available at all point of time, right. So, you may or you may not need, but it is very highly unlikely that you will need double the number of the average, but you may have to find out an optimal number. Again, trade off between utilization of the beds and whenever the patient comes, right, you want to make a bed available to the patient, right. So, it's a basically trade off between these two quantities that you want to have, right. So, this is one simple example where you can use. Of course, there could construct plenty of examples. Another simple one is, let us look at a semiconductor factory where semiconductors are being manufactured in extremely capital intensive fabrication facilities. So, high cost business. This manufacturing of semiconductor devices starts with a silicon wafer and then building the electronic circuitry on that silicon wafers through many process steps. It is not a few, it is many process steps to make it finally the electronic device that you wanted to achieve. So, the objective here could be to determine the flow time, for example, that is a time between a job starts and finishes, right. So, that is what is flow time. So, if you look at in our queuing context, this would be called a sojourn time or waiting time in the system, right. So, that is what it is. So, the past record shows that the factory on each day started on an average with 1000 wafers per day, and it does not get over within a day that the whole process is completed. So, this keeps in waiting, but every day 1000, around 1000 on an average is what we are taking it up. So, the work in process inventory vary between 40,000 to 50,000, so with an average of 45,000, right. So, lambda is 1000 per day the arrival, L, which is number of wafers that are being manufactured, the semiconductors that is being manufactured is basically 45,000 is the L, then W is 45 days, which means you start with one wafer and produce one of this semiconductor, it takes about 45 days. So, this is knowing of this W is critical in the planning and scheduling of these machines, and also whenever there is a demand and to make delivery commitments, right. So, you need to know this flow time or lead time. It may be like 45 days here, and there are certain processes which for which the flow time could be even years. For example, if you look at the steel manufacturing process or anything of that sort, it's a very long period, right, starting from the very basic ingredient of making any product. So, it's a long time. So, it may have to be sourced from elsewhere and everything to be counted and so on. So, in all such scenarios, right. So, this getting to know that you want to get your hands on some information about the system, so that you can play with it and then do to your advantage to make certain progress in the analysis and to make a better system in efficient one. So, for all those things this is a very simple relationship, as we said, but it is very useful, and you will see that throughout many you will use this kind of things in some such systems like handling L or handling W may be very complex, but the average quantity can be obtained through the Little's law. That's the beauty of this quantity. So, now let us look at some more general results that might be of interest to in a particular. This is for both GG1 and GGC systems. Okay. So, again I could see that the lambda is what now we already defined it, but we could take it this to be the average arrival rate in equilibrium. Yes, we already said that it is a random service time and expectation of S. So, the 1 over of this is what will be the average service rate. So, this lambda and mu will be throughout used, right, throughout our course you will use it. So, basically it means that its average arrival rate and the average service rate is what lambdas and mu's. C would be the number of servers, and R which is basically lambda by mu, is called as offered load to the system. So, this is basically the amount of work arriving to the system per unit of time, because lambda and mu are per unit of time. So, the lambda by mu is basically the offered load, which is basically the amount of work arriving to the system per unit of time, and rho, which is lambda by C mu. When there are C servers here, lambda by C mu is known as the traffic intensity or utilization of the server. Sometimes this is also called as offered load to the server. Offered load to the system is R, offered load to the server is rho, but we will call traffic intensity or utilization following that. Okay. Now, with this notation, this Little's law can be used to establish relationship among the performance measure. These are the 4 major performance measure for a typical system, simple system, L, LQ, W, WQ, if that is the case. So, you can see that you can relate these 4 quantities in this manner. Suppose L and W in the normal sense written by L equal to lambda W. Now, if I look at W, which is basically expectation of T, the system time, the mean sojourn time, consisting of mean queuing time plus mean service time, right. Mean queuing time plus mean service time, because my T is basically the time I spent in queue, which is TQ, and the time I spent in service, getting service. So, this is the sum of these 2 quantities is what is my T. So, this expectation is sum of expectation of this is WQ and expectation of this is 1 by mu, and this is expectation of T, right. So, that is what you get. So, from W I can move to WQ using this relationship, right. W to WQ or WQ to WQ, in whichever way it is, you can use relationship. Now, once I am here, now again I can view only Q alone and apply Little's law, then I will get this relationship, as we have already seen, LQ equal to lambda times WQ. Now, once I have this LQ and this LQ, again I use the same idea here, that L equal to LQ plus R, because L is basically lambda times W, W is essentially this quantity. So, that means this lambda WQ is LQ and lambda by mu is R. So, L equal to LQ plus R, right. So, this is what is the relationship between L and LQ. Now, if I get I know the parameters for the model, and if I get say L or LQ or W or WQ, one of those, then I can get the remaining 3 using this relationship. So, this relationship is very important in that sense, right, very useful, generic one. And now, whenever this C is equal to 1, there is a single server system, then my R from here I can write as L minus LQ, which will be equal to simply 1 minus P naught. Since R is equal to rho in this particular case, because my R and rho are like this, when C is equal to 1, this is 1 and the same. So, my P naught is 1 minus rho, which is earlier also we have obtained, if you recall, right. So, that is the relationship that we have obtained, right. Now, this the interpretation, the ratio. So, this is say again, and I will say that all these results are applicable for a GGC system, whereas this last line is for a single server system, that you have this interpretation, right. P naught is basically the fraction of time the server is free is 1 minus rho. Now, this R, which is lambda by mu, can be interpreted as the expected number of customers in service or the average number of BC servers, right. It is obvious, right. You can see that you could give interpretation. So, this in the many situations like this particular offered load is basically represents the minimum number of servers needed to meet a particular traffic demand, right. So, this that is what is offered load, which means this is the offered load. So, the number of number of servers that are needed to serve this particular stream of arrivals must be at least the offered load, because otherwise you cannot handle. But due to variability in the offer load, so you need to buffer up little bit more, but how much is that little bit more is again in a study, different region and different scenarios, you will arrive at different results, and one can show that, that is a different matter anyway. So, but at least it represent the minimum number of servers needed to meet a particular traffic demand, so that stability of the queuing system can be ensured, right. So, similarly this could be represented rho, which is lambda by C mu, can be represented the fraction of time each server is busy. Suppose if this rho is 0.5, which means that only 50% of the time all the server, whether it is single server or multi server, all the servers are each server is how much is the proportion of time that this is particular server is free or busy, it turns out. So, it turns out that for the steady state to exist, rho must be less than 1 or lambda is less than C mu, right. That is what is offered load should be minimum number of servers. So, C should be greater than or equal to lambda by mu, which is essentially is what you need to achieve the stability. Now, on the other hand, if rho equal to 1, unless things are deterministic, okay. If rho equal to 1 and things are deterministic, of course, you are meeting exactly, like server is never free and arrivals are always happening exactly when it is needed, right, just like just in concept that you have, right. So, that is rho equal to 1 case, but if there is randomness, then rho is equal to 1 is not going to work, because due to randomness the queue will start building up and then things will be not in a stable situation. And obviously rho greater than 1 means the number of arrivals, if you look at here the arrivals and this is C server together, like what is the service rate. So, this is the number of arrivals when it exceeds, the average rate of arrivals exceeds the maximum rate of service of the system, then obviously like things are not going to be stable and things will explode. So, that is what. So, for stability or the steady state as we call it to exist for the system, we must have this as the system, this as the condition. Okay. So, that is a thing that obviously in reality the queue will not grow forever, no queue, because queues have certain inner mechanism by which it will turn out. Even if it is you are designing a telephone network or communication network where you are not given enough bandwidth, but you just go, what will happen? Like when the things are full, the remaining calls are blocked. Customers will be complaining that my call is not getting connected, right. But for the system, it is in operation. So, what you have scenario? You have a blocking scenario here. So, there is a natural phenomena that prevents the system to explode. System is not going to explode in any situation. Even if it is traffic, even if it 10-kilometer lane, cars are waiting, after that things will, there is no more waiting, because people will go away, this impatience, balking, right, things. So, there will be other features which will happen naturally, which will make things not to explode. So, but what will happen if things can explode and how quickly and all those stuffs, one would need to look at here, okay. So, you will naturally incorporate those features and then you will make it the feature so that things will become stable and you will analyze a stable situation, which is a stable queue where steady state will exist, and then you will analyze that kind of scenarios, okay. So, that is what we will do when we take it up the queuing models one by one. These are some generic results that we have. Of course, there could be some more, but does it matter? We will come back as and when things will be done. So, there could be some special classes, you will have some special generic results. This is much more generic result because it is applicable for G, G, C, Q, right. That is as and when we encounter that, we will look into that, okay. So, this is what we will have today, and thank you, bye.